Okay, we are going to be talking today about the basic notions and properties of probability. Uh, so, to understand what a probability is, we need to first understand a few other notions that before we can actually explain what a probability is. First of all, you need to have something that ends up with a random outcome, and we're going to call that an experiment. So I have a few examples what that could be. A roll of a fair die, for example. Uh, it will end up with something that will be a random outcome. Tossing of a fair coin, you can do it once, twice, or three times. My example here is tossing fair coin twice. Determining a blood type of a random person. So if you're doing a random blood test. And another example, let's say a random choice of a point, any point from 1 to 1 square. You can achieve that, for example, if you are throwing a darts into some board that has a 1 by 1 dimension, let's say foot or whatever else you like, maybe an inch in this case. So that would also end up with a random choice of a point, right? Again, any one of those experiments could end up with something that we didn't expect, that would be unsuccessful experiment. If that happens, then we are repeating experiment and until we get one of those outcomes that we would expect. Like, for example, if I hit the board outside, if I don't hit the board but I throw a dart and go somewhere outside, then I would assume that's unsuccessful and I would repeat it. Or if I toss a fair coin and ends up on edge, or maybe I lose a coin, rolls somewhere off, and then I can't find it, and that will be unsuccessful, so I'd repeat that experiment. Things like that. And in this particular case, in throwing a dart in a board, I would assume that I'm not aiming anywhere. So again, the experiment would have certain legitimate outcomes and then some outcomes that would be unsuccessful, in which case we would just simply repeat experiment, right? Okay, so the outcome, that's the second notion. The outcome is something coded. So we're not gonna, for example, if I roll a fair die, that die could roll, drop off the table, go on the floor, roll under the desk. I don't know what else can happen, but I'm not interested in all of those details. I'm only interested in what is going to be on the top of that die, and it will have either one indentation or two or three or four or five or six, right? This was usually on the top of the die, some kind of number of points that put that geometrically in some pattern that would indicate 1, 2, 3, 4, 5, or 6, and that's my code. So I'm going to say 1, 2, 3, 4, 5, or 6. I'm not going to describe all of the things that can happen with when you roll a die. The same thing with flipping fair coin twice. I have heads, tails, heads, not the same, and tails, tails, meaning the first flip tails, the second flip tails. Then the blood type I can have 8 different blood types, right? You have the depending on the antigens that is in the red cells, they can be A plus, A minus, B plus, B minus, AB plus, AB minus, O plus, or O minus. So 8 different blood types. So all of these first 3 would have a finite number of things in it, right? The first one has 6, the second one 4, the third example has 8 outcomes. Now, in this example, if I am choosing a random point from 1 by 1 square, I can have infinitely many, because I can have any point here. And now, how would we denote that? We would say, I guess, coordinates of the point, x and y, right? X would be anything between 0 and 1, and y could be anything between 0 and 1. So you have a point like here, for example, that will be point, I don't know, I'm trying to guess, point 8 for an x, and maybe point 8.2 for a y, something like that, right? So again, this would be how many points you have here? Infinitely many, right? So, okay, there could be infinite number of outcomes. Now, when we are collecting all of the outcomes in one set, then that set is called sample space. This is going to be a probabilistic sample space. So we're not talking about samples. We're talking about particular name for set of all of the outcomes of random outcomes of an experiment, right? So you have an experiment, you have a bunch of random outcomes that can happen. Of course, when you have one experiment, one thing will happen, not 10. But collection of all of those things that could happen, we will call a sample space. And that's a set, a collection. So we put the wiggle brackets to tell you that this is now a collection, a set, a bag of all of those things. So in the first example, 1, 2, 3, 4, 5, or 6. In the second example, H, 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 T, T, H, T, T, with the explanation I gave you before. And in the third example, that's the set of 8 different blood types. And in the fourth example, there will be a set of all of the points. This is how we write that. All of the points x, y, when x is anything between 0 and 1, and y is anything between 0 and 1. Anything, any point here, right? Okay, now the fourth notion, and which is the notion that is important to us now for a probability, is a notion of an event. Event is a subset of a sample space. So something that is made out of the portion of a sample space. It could be the whole thing. It could also be an empty set, meaning nothing at all, right? So anything between an empty set that doesn't have anything and the whole sample space is an event. So for example, I could say no less than 5 when I roll a die. That would mean 5 or 6, right? That's an event. So this set of these two outcomes is called an event. And I can also code it, right? I just code it. I said no less than 5. That's English sentence code for the same thing, right? If I say at least one head, when I flip the coin twice, that could mean that I have heads, tails, or tail heads. So that is also an event. 3 out of 4 things here, okay? So it could be anything that contains no outcome at all, that would be an empty event, or the whole sample space. That would be all of that, right? That is also an event. So sample space itself is an event. Negative blood type, for example, in my first example, that would be A negative, B negative, A, B negative, O negative. So that's again a subset, sub-collection of this sample space. In example 3, it's about a half of them, right? Exactly half of them. In case of a sample space, that would be all of the points in this 1 by 1 square. I could have, for example, bottom half. These guys here, these points in the bottom half. So that would be also an event. So what this says here is set of all x, y's points when x is anything between 0 and 1, but y must be something between 0 and a half, right? Between 0 and 0.5. So it's not going to go above that. So that's the bottom half, basically, right? So again, that's an event. I could take anything else. For example, we could use, I don't know, this wiggle, right? That could also be an event, a subset that has points. There are points in this wiggle, so that would also be an event. Anything. So you can see you have lots of events you can have from a sample space. Any subset of stuff that is in the sample space is called an event. Okay, so now we also have a notion, I should say, when you have only one thing, like let's say 5. You're rolling a die and you're considering only the situation when you get 5. That is also an event. It's a singleton event. It has one single thing in it, but it's also an event. So as difference, there is just a semantic difference here. When you say outcome, you mean the outcome of an experiment. When you say an event, you mean the collection of outcomes. So it might be nothing in it, 1, 2, 5, whatever. So when it's 1, you have a singleton event, or a simple event as we call it. Simple event. Okay, meaning only one thing. Okay, so now what is the probability? All right, good question. If you ask anybody what is the probability, the answer that you're gonna get will be, oh, it's a chance, right? It's really not a good answer because it doesn't tell you anything, really. I mean, you're just using a different word to describe the same thing, but you don't really have a definition. You're not being precise about it. Okay, so we would say this is an assignment. Probability is an assignment to an event. So it has to be probability of an event. It's going to be assignment of a number to an event. Now the good question is what kind of number, okay? So definitely that number that is an assignment to an event should be something that you would consider to be a chance of that event happening. So that's the idea. So again, probability is an assignment to an event, an assignment of a number to an event. Very simple, right? Not yet precise, because you can say, oh, all right, I can assign number 35, like I'm in a bank waiting for, my place. No, there will be certain properties that assignment must have, so 33 would not be applicable. Okay, and we'll see that later. But in a case, if the number of outcomes is equally likely, and all of the outcomes are equally likely, and the number is finite, then we have a very simple formula for probability. When you want to calculate probability of an event, again, probability is only considered to be a probability of an event, right? So probability is, this is what you need to do. You need to find out how many things are in the event, because there is a number of outcomes is finite, so it's going to be a finite number. You will be able to count. And then you are going to count how many the outcomes you have in the sample space, the total number of outcomes, and you divide those two numbers. That's it. That is going to be a probability. So that obviously is going to be a number that is going to be less than 1, or maybe 1, right? But no more than 1, because the number of outcomes in the event will never be bigger than the total number of outcomes. It's also going to be something that is not less than 0. It cannot be a negative number, because again, you cannot have the number of outcomes in an event to be negative, and the total number of outcomes in negative is not negative either. So there could be only positive numbers. So it's going to be something between 0 and 1. Okay, and that's our understanding what a probability is. When we say a chance, we always mean something between 0 and 1, right? We will probably say, I don't know, 30%, but that means 0.3. Okay, 30% is 0.3 as decimal number. Okay, but this is only applicable when you have the outcomes that are equally likely and when the number of outcomes is finite, which means in our case, only in the example 1, example 2. If you roll a fair die, it's equally likely you're going to get 1, 2, 3, 4, 5, or 6, and obviously there is only finite number of them. 6 of them, right? 6 different outcomes you can have. Tossing a fair coin twice also. You can only get HH, HT, TH, TT. So a finite number of them. Are they equally likely? Yes, they're equally likely. You can try yourself. Flip the fair coin twice and do that experiment, I don't know, 1,000 times, and you will see approximately 250 times you're going to have two heads and heads. 250 times approximately, you're going to get heads, tails, tails, heads, or tails, tails. Okay, we can argue that by using probabilistic property. We'll get to that at some point, but I think the common sense tells you that they are equally likely, because the heads are equally likely as the tails. So to get heads on the first toss is equally likely as getting tails. To get heads on the second toss is equally likely to get tails. So any of those combinations must be equally likely. All right, so that's My logic, of course. There is a property, of course, a probability that goes with that. Okay, blood type, that is a problem. The number of outcome is here 8, which is finite number, but not equally likely. A plus blood type is approximately in 30% of the population. A minus blood type is, I don't know, 2 or 3% of the population. So this first one is probably 10 times more likely or more. That's why you cannot use that formula. So if I ask you, for example, what is the chance that you would get a negative blood type, you could say, oh, 1 out of 2. It's a 4 out of 8, right? 4 negatives out of 8 total. But that would be wrong, because the formula that we use here for calculating probability requires that outcomes are equally likely. And in the blood type, the chance of getting the A plus blood type is not the same as A minus blood type. And the same thing for all of the others. They're all different. None of them is equally likely to any other, right? You can actually find that distribution if you look at the health statistics of a particular country. And if you go from country to country, it's going to be different. But again, they're not equally likely. Also, in this example of hitting the square or choosing a point from a square, now that's equally likely. It's equally likely to get any point as any other point. But there are infinitely many of them. So that's a problem. So you cannot count. So for example, you'd say, oh, let's see, what's the probability I'm going to hit the bottom half? Obviously 1/2, right? I mean, if I'm hitting this square, if the probability of that is 100%, right? I said already, if you don't hit the square, then you're going to repeat the experiment. So that's not a successful experiment. But if I hit the square, there's equal a chance I'm going to hit the top or bottom half. So I say hitting the bottom half is 50% chance, right? So that's 1 out of 2. But that's not by, I didn't come up with that with counting, because I cannot count how many points are here, nor in the whole thing. So I'm using here the idea of area, because I think the area here is half of the whole thing, right? Now, if you ask me a question, what is the chance to hit this line here? I must be able to answer that, and I should say 0, because there's no area for this line, right? So you have a little bit of a problem here, but you can choose the area. The question is, the area a good choice? Now, if you say any event here, any subset of bunch of points from this square would have a probability that is exactly the area of that, right? So in some cases, you might not have any area, right? So now you're facing something that we know in probability. An event whose probability is 0, but it's not an empty event. Meaning improbable, but not impossible. Not impossible. It's still possible to get a point on this line, but the chance of getting a point on this line is 0. And the reason I'm having here now the probability could be 0, even though the event is not empty. Right? And the idea is very simple, because I'm using the area to describe the probability here. So the area of the event is the probability of the event. Now you could use something else, but probability has to have certain properties. Okay? Those properties. So again, if you cannot have equally likely outcomes, like in the blood type example, or if you cannot have the number of outcomes finite, like that 1-to-1 square, when you have infinitely many points, then you cannot use this formula. Only where the outcomes are equally likely and the number of all of the outcomes is finite, so which means the sample space is finite. Then this formula is to be used. If you do not have that, one of the conditions missing or both, then you cannot use this formula. So what's the probability in that case? Well, we could define probability in that case if we could talk about distribution function differently. we will not be talking in this class of ours about distribution function. But there's a way to do that. However, we can also require the probability. You can come up with anything you like, but the probability needs to have the following property. This was defined or found out, if you like, in 1930 when the if I would try to pronounce Russian, I would say Kolmogorov wrote his book Foundations of Probability, or Foundation of Probability, I think. That's the name of the book. In which he was saying, okay, you can have anything you like, but it needs to have these properties. And if it fails any one of those properties, you don't have a probability, you have something else. Right? So the area would be in that 1-to-1 square, would be probability. And we'll go through this property so you can think about it separately. But the again, the probability is defined on an event. So we're going to write like that: probability of this. The symbol is for of some event. Now we can call that uppercase Latin characters. So it could be A, B, C, anything. I use E here in the description because I'm just abbreviating event, or A, or anything else. Okay? So again, probability is an assignment of a number to an event, a number. Okay? The property number 1, that assignment must be between 0 and 1. So we already discussed it a little bit in that formula, but on any probability you want, it has to be between 0 and 1. So area case here, it's going to be between 0 and 1 because the area of 1 by 1 whole thing is 1. So it could be anything smaller if it's a smaller event, right? And it could not be negative because area cannot be negative. So this is what it has to happen. So number 1, the area, or area, the probability will be for any event an assignment, and it will be between 0 and 1. Okay? I said this is self-evident property. It had to be clear that if you're going to declare a chance of something, it'll have to be between 0 and 100%. And that in decimal writing, and you write this decimal number, is going to be between 0 and 1. Okay? Then there is a property number 2, which says the probability of an event complementary to that event, when you add them, it has to be 1. What's an event complementary? An event that is complementary is the opposite. Right? When I'm saying, well, I'm going to have at least one head, then I'm talking about getting heads on any of the tosses, right? That would, complementary to that would be the opposite. That would be, we don't have any head. So that's all tails, right? That's a complementary event. It's just simply opposite to whatever the event is. So, for example, I'm crossing the street. That's an experiment. I'm going to get hit by a car. That's an event, right? Opposite to that would be I'm not going to get hit by a car. And of course, if the probability of me getting hit by a car on the passing the street is 0.1%, then the probability of the opposite event must be 99.9%. So they ought to add up to 1. That's another self-evident property stated here. So again, probability of an event that is complementary, they do have a probability, and those probabilities, when you add them, must be 1. So if the first one doesn't happen, that means you have the second one. If the second one doesn't happen, that means you have the first one. So the probability of both of them, has to add up to 1, which I'm also saying that the probability of the whole sample space must be 1, right? Okay, so why am I saying that? Because the probability of a sample space is probability of everything. And complementary to the sample space is an empty set, nothing in it, right? And they both ought to add up to 1. So it's self-evident to me that nothing will happen, the probability that nothing will happen is 0. So the probability that something will happen is 1. That's a sample space, right? So again, that's some sort of self-evident property. Probability has to have this property. And here is an example. If I flip the coin 3 times, these are the outcomes I'm going to get. HHA roll 3 heads, then you get HHT, HTH, HTT, THH, THT, TTH, TTT. So you wonder, how did you list that all? Well, it's actually easy. So the first toss, you either get head or tail. The second toss, you can branch that out. You either get head or tail. And then you have the third toss, and again you can get head or tail, heads or tails. Okay. And any of these pathways, the things that could happen when you toss the fair coin 3 times, one of the pathway will be done, right? So for example, you have a tail on the first toss, heads on the second toss, and tail on the third toss. So you have this pathway. Okay? So you can go to the pathway 1, 2, 3, 4, 5, 6, 7, 8. THH, so that's the 6th one here, this guy. That's exactly what I did. That's how I list them, right? Okay, but one way or the other, so I said at least one head. What's a complementary event? Again, no heads at all. That would be all 3 tails. So this is the complementary event. And this is the event at least one head. At least one head, no heads at all. Right? So they're complementary, meaning they cover everything, but they have nothing in common. Easy to understand, right? The probability must be adding up to 1, which is easy to see. These are all equally likely, and there is 8 of them. So we can use the formula. This one. They're all equally likely, and there are 8 of them. And the formula would tell you that the chance of having at least one head would be 7 out of 8, or 87.5%. If you divide 7 with 8, you're going to get that number, 0.875. And it's easier to calculate what's the probability you're not going to have any head, because you have only tail, 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 and that would be 1 out of 8, and that's 12.5%. So if you calculate that first, then the other one must be 87.5%, because that is 100 when you add. So sometimes it's easier to calculate complementary event probability, and then after that you can conclude what is the event of the probability of the event you're interested in. But we, again, this is really not a hard calculation. We can just simply use this formula: 7 out of 8 and 1 out of 8. Okay. Another property. If the events are mutually exclusive, and the events are mutually exclusive and they have nothing in common. So 2 complementary events are always mutually exclusive, because they're not going to have anything in common. No outcomes in common. But the mutually exclusive events don't have to be complementary, meaning they don't have to have everything in it, right? One could be made out of those eight things. One could be with 3 of those 8, another one could be another 2 of those 8, but nothing in common. But they don't cover everything, because 3 and 2, it's not 8. Okay, so I'm having here an example that says, let's have a flip of fair coin 3 times, like I already did here, right? This story. If I flip fair coin 3 times, I get exactly this as my sample space. these 8 possible outcomes. And let's say the first event be at least 2 heads. So event A is at least 2 heads. So this is heads, 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 tails, heads, tails, heads, and tails, heads, heads. And let B, the other event, the next event, be precisely 2 tails. Now that will be HTT, so you have 2 tails, THT, 2 tails, TTH, 2 tails. This one doesn't count because it's not exactly two tails. All right, so these 2 events have nothing in common. You can see here, the first event, the event A, is made out of these 4 guys. The event B is made out of these 3 guys. And something is not in either one of them. Okay? They are mutually exclusive. They don't have nothing in common, but they're not complementary because they don't cover everything. So you can see that on this picture here. So precisely 2 tails. One here, another one here, another one here. So that will be this, precisely 2 tails. And at least 1 head, that will be 4 of them. Excuse me, at least 1 head. At least 2 heads, right? That's what's the event A. At least 2 heads, right? Not 1 head. Then I would not have them exclusive. So these are the events. So this is my A, and this is my B. You can see they have nothing in common, right? There's no any outcome that is in both of them. But they are not complementary because this guy is outside of either. So they're not complementing each other. Something is missing here. Okay? They're not exactly opposite, right? Okay, what is the property that I really want? Is that probability of A or B must be probability of A plus probability of B. What does that say is that if you are looking for a probability of at least 2 heads or precisely 2 tails, you're talking about the 7 guys. At least 2 heads, 1, 2, 3, 4, or precisely 2 tails, 1, 2, 3. So the event A or B, that's an event, it has 7 things in it. A or B is an event. You can call it C if you like, but you can just simply call it A or B. That's an event that has 7 things in it. The same as the probability of A plus the probability of B. Okay? And it makes perfect sense. You can see here, it's got to be this 4 and this 3. So the probability of A is 4 out of 8. Probability of B is 3 out of 8. And the probability of A or B is going to be 7 out of 8. Makes perfect sense. So if you add 4 out of 8 and 3 out of 8, you get 7 out of 8. You can, of course, you can call this 1/2, but you know, when you're adding a fraction, you like to have the common denominator. So that's why I wrote it this way. This property must hold. Again, it's one of those properties kind of self-evident. Here, obviously. But for any probability that must happen, even if it's infinitely many outcomes, not equally likely, whatever, it has this must hold. This property must hold. And it makes perfect sense to us that this property holds. Now, if you're talking about any kind of sets that are not necessarily mutually exclusive, so events, they might have some overlaps, okay? Then we have a different property. That property says the probability of A or B must be the same as probability of A plus the probability of B minus the probability of A and B. Okay, so there is an event A or B, and there is an event A and B. When you add them up, it's the same as if you're adding probability of A, probability of B. So when you add the probability of A or B, probability of A and B must be the same as probability of A plus probability of B. I mean, this is the same equation. You just put this term, this is the number here with negative, put it on another side, you're going to have positive, right? So this is the same thing here. This property you can write in 2 different ways. but uh, it must hold. Okay, so let me give you an explanation for this, and this is an example. If you have an experiment that is a roll of 2 dice, these are the outcomes you're gonna get. You're gonna get the 1 1 1 2 1 3 1 4 1 5 1 6 2 2 2 1 2 2 2 3 and so on. What does that mean? For example, this one means 3 on the first roll on the first die and 4 on the second roll on the second die. So we can talk about 2 dice, or we can talk about first roll and the second roll of the same die. You can say this would be the same. No, it isn't, because this would be 4 3. You can have two different dies. You can even have them in different color. The one black with the white dots and the one white with black dots. So this will be 3 is on the black one and 4 is on the white one. This is 4 on the black one and 3 on the white one. Not the same thing. Okay. Some people get confused with that. It's not the same thing, right? Or if you roll one die twice, there will be 3 on the first roll, 4 on the second, 4 on the first, 3 on the second. Not the same thing, okay? But you have 36 events. If you can find any more, let me know. 36. Okay? So we are talking about the 2 different events that are not necessarily complementary. I decided to have A to B. The sum of both is no more than 8. That's this stuff here, okay? No more than 8. That's precisely this stuff here. This is no more than 8, no more than 8. This is 8 exactly. 8 exactly. 8, 8, 8, that's it. This is no more than 8, right? This is more than 8 here. You got 12, you got 11, you got 10, and here you got 9. Okay, so that's an event A. Okay, let's have an event B to be at least 1/6. Now, if you're going to have at least 1/6, we're talking about these guys. Okay, this is the 6 on the second roll. This is the 6 on the first roll, or the first die, if you like. And this is the situation when you have both of them 6. But there are 11 here, right? And there are 26 here. If you want to count, it's going to be 26 here. It's easier to count 10 here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 36. So the red part has 26 things in it. So the blue part is the event B. At least 1/6. 8 is no more than 8. Right? No more. Sum is no more than 8. You can see these 2 events are not complementary. They're not mutually exclusive. They don't cover everything, and they have something in common. Okay? So when you say when you want to find out probability of A, these are all equally likely. It's equally likely to get any number on the first roll, on the first die, any number on the second die, and there are 36 of them. So we can use a formula. The probability of B, it's easier to calculate here because you have less to count. That's clearly 11 out of 36. I need to squeeze this. All right? That's the probability of B. What's the probability of A? Well, the probability of A, apparently, it's going to be a count of these guys here divided by 36. So the probability of A, and I told you there are 26 of them. Probability of A is going to be 26 out of 36. Again, I'm using that formula. It says you have finite number of them, and you have all of them equally likely, then you count this way. How many you have in the event, how many you have total. Okay? Now what would be the probability A and B? That would mean you have at least 1/6, and you also have sum that is no more than 8. So that's this, this. What is in the intersection? What is in the overlap? It has to be in the event A because it has to be no more than 8, and it also has to be in event B because it has to be at least 1/6. So no more than 8 and at least 1/6. So these are the 4 guys here. Okay, so we have the probability of A and B to be 4 out of 36. A and B. Okay, I hope you're familiar with this symbol for an and, because I have to squeeze, I don't have much space here. That will be 4 out of 36. Okay. How about the or? A or B. That means at least 1/6 or no more than 8. That means all of these guys that are in either one of them. That should be A or in B. This one fits. At least 1/6. It's more than 8, but it's at least 1/6. We're not asking both. We are asking no more than 8 or at least 1/6. And I'm not exclusive here. So if you have both, it's fine. So all of these guys, there are 33 of them. So probability of A or, now I'm going to use the English symbol. I don't have one. Okay, so I have to write or. We do have the symbol in logic for that. We use 2 bars in the computer science. We use in logic we use V, but okay, I'm just going to write or. And I said this is going to be 33 out of 36. So what's the property that I said it has to be? The property says that when you add these 2 guys, it must be the same as if you add these 2. Okay, if you add this and this, you got 26 plus 11, that's 37 out of 36. And when you add these 2, you also get 4 plus 33, 37 out of 36. That happens. So, yes, the property holds. Again, I mean, this would be property A or B, so B, A or B, 33 out of 36. Probability of A plus probability B would be 26 plus 11, that would be 37 out of 36. Minus probability of A and B, that would be minus 3, that would be 37 minus, what was that? I was saying, ooh, I made a mistake here. A and B is 4. Yeah, I didn't count well, right? 4, okay. I just realized, because the property must hold, this 33 out of 36 is probability of A, 26, plus probability of B, 11, that would be 37 out of 36, minus probability of A and B, minus 4, that's 33. Yeah, the property holds. It makes perfect sense when you even think about area. If you think about the area, it will be for that rectangle we have. That makes perfect sense. How do you get the area of A or B? Oh, okay. You got the area of A or B. It's gonna be the area of A, the area of B. But now when you add those 2 areas, you have something twice because it's in the A or in the B. So you have to remove it once. So the probability is an area, that makes perfect sense here. Okay? This property must hold regardless. Again, whether it's self-evident or not, but it must hold. Probability must have this property. Okay, so that's a Kolmogorov definition of probability. Probability must have this property. If it doesn't have, it's not a probability. Okay, so he was approaching that from the point of view, okay, I'm going to give you the property of probability must have. So anytime you have that, that's a probability. If you don't have that, it isn't. Okay, and because it fits all of our notion of probability, tested over a period of time, right? We know, we accept that. That's exactly what we expect probability to have as a property. Okay, One more, or two more, I should say. Uh, Independent event. When you have independent events, well, you need to know what an independent means. Independent means that the two events have nothing not necessarily something in common, or not, they might have something in common, but they have no influence on each other. So, for example, if I roll a die, the first roll I could have anything between 1 and 6, and then I roll the second time. I could have again anything in between 1 and 6. Whatever happened on the first roll doesn't have any impact on the second roll. It won't change anything, right? So those two events are independent. Whatever happens on the second roll will have nothing to do with the first roll. So if I have a 6 on the second roll, that doesn't mean that I might have more likely any 6 on the first roll, or 3 or 5 or whatever. They are independent. Okay? Not every events are independent. So, for example, if I give you 4 aces, 4 cards with aces, ace of spades, ace of diamonds, ace of what is it, clubs, what else we have, aces, diamonds, clubs, something else, right? So we have 4 different aces: spade, clubs, diamonds, hearts. Now I know. Okay, 4 aces. What's the chance that at random, you don't see my aces, what's the chance that you're going to pull out the ace of spade? You must have 1 out of 4 chance, right? Because the 4 different aces, so to pull that one is going to be 1 out of 4. Okay? Now let's say that you remove the ace of diamonds. The chance of getting ace of diamonds is 1 out of 4. Now what's the chance that you're going to have now ace of spade? Now it's 1 out of 3. So pulling the ace of diamonds, or the ace of diamonds is the probability of pulling one card out, will have an impact on the probability of getting ace of spade. It will increase the probability of getting ace of spade in the second drawing. Okay, so those two events are dependent. I'll give you another example. This is kind of like a strange example. Let's say if I am going to entertain myself tonight, I could probably play chess, or I could watch a movie, right? Now, if I play chess tonight, the chance of me watching a movie is very slim, because I can't really watch the movie and play chess. Maybe some people can, but I can't, right? So if I tell you that I'm going to play chess, then you know that there's 0 chance he's going to watch a movie. Okay, if I didn't tell you that, the chance of me watching a movie or playing chess, I don't know, maybe 50-50. Okay, so those are dependent events. Okay, flipping a fair coin the first time and the second time are independent events. Whatever happened the first time, whatever happened the second time will be independent. Okay, those are independent events. So Kolmogorov says this, this mathematician that defined this. It says, if you have independent events, probability of A and B is the same as probability of A times the probability of B. Okay? Probability of A times the probability of B will give you the probability of A and B. So this is an event. A and B is an event. A is an event. B is an event. To get the probability of A and B, you just have to multiply the individual probability of A and the probability of B. Okay? So I have an example. Let's have the roll of 2 dice. Okay, so we have this story here, but different. I'm going to have a different events now. And I say, let's the first event be 6 on the first roll. Okay, 6 on the first roll. That will be this one. Six on a second roll will be this one. Okay, each one of them is 6 out of 36, so you can say 1 out of 6. You already know what is the chance you're gonna have a 6 on the first roll. 1 out of 6. You can see here as well. If you flip the coin 2 times, 3 times, whatever, the chance to get a 6 on the first roll will be 1 out of 6. Or if you flip it twice, it's gonna be a coin. Excuse me. Roll the die. Roll a die, a fat die. Probability of getting 6 on the first roll is gonna be 6 on the first roll is B actually. All right. Maybe I should change the names. I was not very careful. So let's say we're gonna call these A, and we're gonna call this one 6 on the second roll B. Sorry about that. Okay. 1 out of 6, 6 on the second roll, 1 out of 6, 6 on the first roll. What you see here is 6 out of 36, but that's reduced to 1 out of 6. Which you should know by experience, right? Now, the chance of getting A and B means 6 on the first roll and 6 on the second roll. That's only this guy, right? And the probability of this guy is 1 out of 36. So we have here probability of A and B 1 out of 36, probability of A is 1 out of 6, probability of B is 1 out of 6. And if you multiply probability of A and probability of B, you're going to get a probability of A and B, which is 1 out of 36. Makes perfect sense. But I'm saying that this must hold every time the events are independent. And pay attention again, these two events are not exclusive. I mean, they have something in common. Okay, so events being independent doesn't mean they're exclusive. They don't have to be mutually exclusive. Mutually exclusive events, they don't have anything in common. But these two events have something in common. But they're still independent. Okay, so independence is something different. It's not mutually exclusive. Mutually exclusive one notion, independence is another notion. Again, independence means that the event has a probability of happening, occurring, regardless of the other event occurring or not occurring. So the chance of getting 6 on the second roll makes it's 1 out of 6 regardless what happened on the first roll. Whether you have 6 on the first roll or not will make no difference, right? And again, I said that is in this case, but sometimes the events are, when they are not independent, they are dependent. Like if I play chess tonight, I will not watch a movie. I can't do both, right? Or vice versa. If I watch a movie, I'm not gonna play chess because I already know I'm playing lousy when I'm not fully concentrated. So I will not play. Nobody likes to lose, right? So again, so this is the notion of independence. Probability of occurrence of one has no impact on the probability of occurrence of the other one. Okay, that's important. When that happens, when that changes, and if you are having two events that once you know the first one happened, then the second one is more likely or less likely, then they are dependent. Okay. So that's the idea of independent events. But Kolmogorov says if you have independent events, this must happen. As a matter of fact, he went vice versa. He said when this happens, the events are independent. But I mean, the property must hold. Okay? But what do you have when you have two events that are not necessarily independent? So any two events, independent or not independent, then this must happen. This is a property that is critical. It has to be holding for any two events. Says here, let's have the event A to be sum on both is 10. Sum on both is 10 is this 3. 6, 4, 5, 5, 4, 6. So that will be 3 out of 36. The probability of A is 3 out of 36. You can see 3 out of 36. That's sum being 10. There's only here 4, 6, 5, 5, 6, 4. Okay, so let that be A. Let B be at least one die 6. Now we already have that. So that's this, and this. So that will be 11 out of 36. Okay, so probability of B is 11 out of 36. Okay, now what this property says is probability of A and B. Probability of A and B are the things that are in common. So that's this guy and this guy. So that'd be probability of A and B is 2 out of 36. 2. This guy and this guy. When you say, I have at least 1 6 and the sum is 10, we're talking about 4 6 or 6 4. 2 out of 36. So that's a probability of A and B. Again, A and B is an event. There's a certain number of outcomes there. 2, actually. Okay, probability of A, we already justify that to be 3 out of 36 because in the 3 things in A. Okay, what the heck is this? Probability of B given that A has occurred. So you have some condition here. A has happened. What's the probability of B? Okay, so if I'm telling you the sum is 10, what's the chance to have at least 1 6? That's what this means. This is a conditional probability. It is a probability, but it's a conditional probability. So what is the probability of B given that you have an A? So I'm saying we have a sum. I'm hiding 2 dice from you, but I'm saying to you the sum is 10. What's the chance I have at least 1 6? You're going to say, yeah, if the sum is 10, you have these 3 guys. What's the chance you're going to have at least 1 6? It's here and it's here. 2 out of 3. So the probability of this is 2 out of 3 in this case. This is a conditional probability. You have to think here. You're not going to be 2 out of 36. It's going to be 2 out of 3. Because I'm telling you that we have one of these 3. We have sum 10. So it's one of these 3. The whole sample space has been now reduced to the A. What's the chance you're going to have at least 1 6? Well, you can have either this or you can have this. 2 out of 3. So this is a probability, 2 out of 3. And this is a probability we already said, 3 out of 36. Now if you multiply this and this, you get exactly this guy. You can try it. So you have to multiply 3 out of 36 times 2 out of 3. And if you know something about fraction, you can cancel this one, and you end up with 2 out of 36. Interesting. So probability of A and B must be the same as probability of A times the probability of B with A condition. So given that A has happened. Okay? Right? So that is kind of difficult property to swallow. It's something special about it, but it must hold for any probability. Probability doesn't have this property, too bad. Okay. Conditional probabilities are very often in the game. You can ask, what's the chance that Roger Federer beat Novak Djokovic in a final when you know that he won the first 2 sets? That's a conditional probability. I'm asking for probability, what's the chance that he wins now one of the remaining 3 sets if they play 5? If you already know that he won 2. So that's a conditional probability. So very often you have a conditional probability. What's the chance that this is going to happen if we know something, right? So that's a conditional probability. And so this property says, if you want to calculate A and B, probability of A and B, and they're not necessarily independent, then you just simply have to multiply probability of A and probability of B given A. Or vice versa. You can multiply probability of B times the probability of A given B. You can replace the order. Probability of A and B is the same as probability of B and A. Right? Again, I know this is kind of difficult property to understand, but it's the property that must hold. And by the way, these two events are dependent. Now, if I told you that you have a sum 10, then you know immediately there's a pretty good chance I have 1/6, right? 2 out of 3. Now, if I didn't tell you that, the probability you have at least 1/6 is going to be much smaller. It's going to be 11 out of 36. Probability of getting 1/6 on a roll of 2 dice is not that great. 11 out of 36. It's less than 1/3. But when I tell you that the sum is 10, then you know it's 2 out of 3. So these two events, this A and this B, are dependent. Because when you know that one has happened, that increases the chance of the other one. So they are not independent. Okay? Again, we use lots of symbols and notation here that of some importance to us. So we are going to have a little more. Okay? So when you talk about the event complementary to an event A, we usually write an A with a superscript C, which would mean complementary. It could also, in a computer science, people in a computer science, so they use logic and the probability a lot. So they write like that. Means not A. So the A and the not A, that's a complementary event. Okay? In philosophy, when they use logic in philosophy, they write something like this. They also mean the same thing. Sometimes in a computer science, people write like this. It all means the same thing. Not A. Complementary to A. So that's an event complementary. If we use a C as a superscript, that would mean the same thing. Sometimes people even use bar on the top of it, or we won't do that because we have a bar for a particular thing, right? So we won't do that. Okay. When you say or, that's an English word. So in some other language, it's going to be something else. So we write like that: A union B, A or B, A union B is usually the symbol that is used. Sometimes people use this symbol. Okay, I'm not going to bother you with any symbols, so I will not use extra. I will use this one. That means or again. When you mean and, then I was using so far in this lecture, I was using this symbol, which is a English symbol, and people around the planet don't use that. It's just, I mean, in people speaking English, they use this kind of symbol. I don't know why. I don't know where it's coming from, but that's an and. You can use that, or you can use this one. And in logic, people use this. Okay, in computer science, they use 2 vertical bars, so also a different symbol that is used. This is a symbol for intersection in a set theory, so you can use that. That would mean and. Okay, so when you see this, that will mean and. A and B. This would be A or B. Or you can just simply use this guy. And sometimes computer science, to confuse you even more, they use this for and. Twice. For whatever reason. Alright. But again, so those are the symbols. When we have the symbol for a sample space, we use the symbol for a sample space to be either S, uppercase S, sample space, makes sense, abbreviation, or we use a Greek omega. That is also a symbol for a sample space. So when you see this symbol, it's used for nothing else but the sample space. So when you see the symbol, it means actually a set of all of the possible outcomes. Now, this is a symbol for an empty set. So again, this is when you say nothing has happened. Okay, experiment must end up with an outcome, so the probability of nothing has happened is 0, but we use that as an event, just to complete all possible subsets you can have. The 1 thing, 2 things, from 3 things, whatever, the whole thing, and nothing at all. Okay, so that's a notation for an empty set. Means set with no outcomes, event with no outcomes. Probability of empty sets of no outcomes is 0. That's actually complementary to the sample space, right? Because everything is in the sample space. So when you say complementary to sample space, it's going to be empty set. Okay, so we already said that we have a notion of complementary. That means that A or B is the whole sample space. They cover everything. A and B is empty. They have nothing in common, right? Then we said that mutually exclusive, two complementary events are always mutually exclusive, but mutually exclusive do not necessarily mean that they have everything in it. Might be something missing. So you have like 3 in one, 4 in another one, but there's something outside. Okay, they cannot have anything in common, but they don't necessarily cover everything. And then we said also events are independent. When knowing that one has happened, or one has occurred, has no impact on the probability of the other one. The other one, probability of the other one is the same. Okay, I'll give you one more example, but this is the notation we use for the conditional probability. This means probability of A given that B has occurred, B has happened. Okay, this is probability of B given that A has happened. So probability of A given that B has happened must be the same as probability of A. So which means that B has no impact on A. Okay, the probability of A. A probability of B given that A has occurred must be the same as probability of B, regardless whether A has happened or not. Okay, that when you have this, then you have independent events. If you don't have that, then the events are dependent. So opposite to independent is dependent. Okay, and most of the time events are dependent, but sometimes they're independent. So you need to know when. So you have the property number 6 talking about the in general. They could be dependent. Property number 5 talks only about independent events. Okay. Property number 4 talks about the any kind of events, 2. And property number 3 talks about events that are mutually exclusive. Property number 2 talks about events that are complementary. And property number 1, just general notion of probability must be between 0 and 1. Right? So you have 6 properties. As a matter of fact, when you think harder, you'll find out that this one follows from number 4. Because if the events are mutually exclusive, they have nothing in common, then probability of A and B is 0, because they have nothing in common. So there's nothing in A and B. So which means that this would be just simply missing, and then you have the first part here, which is exactly what you have here. The same thing here, the property number 5 follows from property number 6, because when the A and B are independent, the probability of B given A is just the probability of B. So you have probability of A times probability of B is equal to probability of A and B, which is just here. Right? So property number 5 actually follows from property number 6. So you really don't need 6 properties, you need 4. Okay? And to be honest, I mean, Kolmogorov, when he was writing down, he actually only had 3. But here's a more complicated situation, because he also talks about having infinite number of events. We're not going into that. When you can use that notion, then of course you can get a really concise set of properties. Only 3. He has only 3 for probability. But probability must have the 6 properties.